All right, let's jump right in. When you think about all the materials that make up our world, you've got some that are super tough and rigid and others that are soft and bendy. But what if you could take two totally different materials and fuse them together molecule by molecule to create one single super material? Well, that's one of the holy grails in chemistry, a really tough puzzle to solve.
I mean, really think about that. It's like oil and water. You have one kind of plastic that's structured and strong, and another one that might be sticky or super flexible. Now, on their own, they're great. But if you could chemically stitch them together into one single long chain, what chemists call a block copolymer, you could create materials with the best properties of both. The question has always been, how do you actually do that?
And the answer, as we're about to unpack, comes from this incredible new research published in the Journal of the American Chemical Society. And honestly, it's a story that feels like something out of a sci-fi novel. Swapping out a super precious metal for a common one, and then using a simple flick of light to unlock a whole new world of chemistry.
So, to really get why this is such a huge deal, we first have to understand the problem they were up against. And like a lot of things in cutting-edge science, it all boils down to two things: cost and scarcity.
You see, for years, the only way to make these amazing materials was with a catalyst built around palladium. Palladium works like a charm, but it's a precious metal. It's unbelievably rare and super expensive. So the obvious goal, the dream really, was to use nickel instead. I mean, nickel is thousands of times more common and so much cheaper. There was just one tiny problem. For this very specific job, nickel was a total dud. It just didn't work.
This right here, this is the before picture. Take a look at that top reaction, the one labeled A. You see that little symbol PD right in the thick of it? That's our palladium. That's the catalyst that made all this possible, but it's also what made it so incredibly expensive. This was the best they could do.
So if nickel is the cheaper, more sensible choice, why weren't people already using it? Well, it wasn't for lack of trying, believe me. Scientists have been trying to solve this puzzle for years, but for this delicate two-part reaction, it was just one failure after another. So before trying to reinvent the wheel, the team did the logical thing. They tried all the usual suspects. What you're seeing here are the four main types of nickel catalysts, the workhorses of the chemistry world. You've got your Brookhard type, Ni1, the Shop catalyst, Ni2, the Grubbs type, Ni3, and the Levine catalyst, Ni4. They lined them all up and put them to the test.
And this table tells the whole story. The results? They were terrible. I mean, look at this. Under the exact conditions they needed, two of the catalysts gave 0% conversion. Zilch. Nothing happened at all. And the other two? Barely made a dent. The big takeaway here was crystal clear. The standard tools in the toolbox just were not going to work.
And this is where the story takes a turn. Because when the old tools don't work, what do? You have to go back to the drawing board and design something completely new. You have to invent the right tool for the job.
And here they are. These are the heroes of our story. They're called carbyl iminopyridyl nickel complexes. Now, don't worry about that mouthful of a name. Just look at the structure. You've still got that nickel atom, the Ni, sitting right in the center. But it's wrapped in this very specific, really carefully designed organic cage. And that cage, that's the secret sauce. That's what gives this catalyst a superpower that none of the others had.
And hey, you don't have to take my word for it. The researchers themselves, right in the abstract of the paper, call its behavior unprecedented and unique. It has a special selectivity, which basically means it can choose to do one of two very different jobs. And that choice, as we're about to see, is the key to everything.
Okay, and this brings us to the coolest part of this entire breakthrough. This new catalyst doesn't just do one thing well. It does two completely different things. And the way it switches between them is with a simple flick of a switch, a literal switch made of blue light. This diagram gives you the bird's eye view. Over on the left, you see the insertion pathway. That's what the catalyst does when it's dark. It just builds the first type of plastic, that blue chain. Then, see that light bulb icon? That's the switch. You turn on the light, and the catalyst completely changes its behavior, starting the radical pathway over on the right, building that second, red chain. So let's just break that down into 3 easy steps. Step 1, you're in the dark, and the catalyst is just working away, building that first block of polymer. Step 2, you flip the switch. You just turn on a simple blue LED,
And step 3, the moment that light hits, the very same catalyst stops what it was doing and starts building a totally different polymer block right onto the end of the first one. It's incredible.
Okay, let's zoom in on the chemistry for a second. In the dark, the reaction follows this top pathway here. It starts with our catalyst, which is labeled I. It just grabs a molecule, stitches it onto the chain, and moves on to the next one. It just keeps doing this over and over, adding one link at a time to build out that first polymer chain, which they've labeled Pol.
But then comes the magic. After that first block is made, they add the second ingredient. The catalyst grabs one, forming this intermediate here, XIX, or X, and right at this moment, the blue light hits it and snap. It literally breaks the bond between the nickel and the carbon atom. This creates a super reactive end on the polymer chain, and that reactive end starts grabbing the new, red molecules like crazy, building the second block at lightning speed.
Now, that's an amazing story. But seeing is believing. How did the researchers actually prove that this light switch was really working as perfectly as they claimed? They needed some cold, hard data. And this chart right here is the smoking gun. It's so elegant. Just follow the line. When the light is on, the line goes up. The reaction is happening. The very instant the light goes off, the line goes completely flat. The reaction stops dead in its tracks. They can turn this chemical reaction on and off as many times as they want. It's a perfect, controllable switch. Truly remarkable. And here's the final piece of definitive evidence. This analysis basically looks at how fast molecules are moving. So in the graph on the left, when you just mix the two plastics, you get two distinct signals. Makes sense, right? They're two separate things. But now look at the graph on the right. This is the material they made with the light switch reaction. You see that? Just one single unified signal. This is the killer proof that the two chains aren't just mixed together, they are chemically bonded into one single brand new molecule. And this technique isn't just clever, it is seriously powerful. The team was able to create absolutely massive polymer chains, getting up to a molecular weight of 244 kilograms per mole. I mean, that is a gigantic molecule. It just goes to show how effective and reliable this new nickel-powered, light-driven process really is. Okay, so that is some undeniably cool chemistry. But let's zoom back out for a second. Why does any of this really matter? Why should we care about making these specific plastics more cheaply? Well, this single discovery opens up so many doors. It's a direct path to making high-performance materials affordable. We're talking about advanced glues that can bond things that were impossible to stick together before, or special additives called compatibilizers that could let us finally mix and recycle different kinds of plastics together, a huge environmental win. And of course, by using cheap nickel instead of precious palladium, the whole manufacturing process becomes way more sustainable. We can basically start designing new materials from the ground up. And all of this leaves us with one last fascinating question to chew on. This research proved that you can use light as a precision tool to tell a catalyst what to do. So it makes you wonder, what other complex reactions, what other miracle materials are just sitting there waiting for us to discover the right way to flip the switch?